Welcome to my YouTube channel. Please don't forget to subscribe, like, and share. Understanding the development controls. Under Rules 7 and 8 of the Revised Implementing Rules and Regulations of PD number 1096, National Building Code of the Philippines.
Today, we'll be diving into part 5 of my series on development controls, focusing on the Allowable Maximum Volume of Building, or the AMVB, which is the most tedious of all development controls to derive. So stay tuned. So for our example, we are going to use the one from our part 1, which is the single detached house in an R1 zone property with a total lot area of 301 square meters. So it is an inside lot with a 14-meter wide frontage facing south to a 12-meter wide road. So the development controls on the AMVB can be derived in two ways. One is basing it on the AMBF and the BHL, which is our initial value for the allowable maximum volume of building, or the AMVB initial, or the AMVB plainly that is based on the AMBF and the BHL. So another way to compute for the AMVB is to compute it that will satisfy natural light and ventilation requirements along road right-of-way and front yards. So it means here that you are going to make use of the angular plane emanating from the center of the road. So let us first compute the AMVB based on the AMBF and the BHL. So we are going to make use of our value of the AMBF, which is 150 square meters, and the BHL. So as per table 7.2, our BHL for R1 in meters will be at 10 meters above the highest grade. So simply, the AMVB here is your AMBF, and we multiply it with the BHL. And so, our value therefore for the AMVB will be the AMBF of 150 times the BHL of 10 meters will now give you an AMVB of 1,500 cubic meters. So this is the initial value of the AMVB, or simply your AMVB that is based on your value of the AMBF and the BHL. So to illustrate this initial value of the AMBV, so we have this axonometric drawing of your lot. We have a TLA of 301 square meters, 14 meters by 21.5. And if we draw the AMBF there at 10 times 15, or 150 square meters, and then project that AMBF to its building height limit of 10 meters, 10 meters according to the table for the BHL, we will arrive at this volume, and that will be your AMVB initial at 1,500 cubic meters. Now, there is a requirement in the code that an angular plane is to be considered emanating from the center of the road right-of-way. So if that is the case, then there is a possibility that a portion of this volume of building will be chopped off because it will be extending beyond that angular plane. So if we are going to consider this angular plane, there is that portion of that volume of building which will be chipped off because it will be extending beyond that angular plane. So if that is the case, then we are now going to compute for the second AMVB value, and that is our AMVB that will satisfy natural light and ventilation requirements along road right-of-ways and front yards. So to do this one, it will be best to make a cross section of the site. However, we have to consider the slope of the site and the width of the road. And this problem will have this additional information that the site uniformly slopes down at 15% towards the 12-meter wide main street, and that the surface of the sidewalk at the center of the site frontage is considered as elevation 0. So let us draw a section of that site. So we have the road at 12 meters and the sloping site at 15%. So we draw from the center line of the road, that is at 6 meters. And then from the front property line to the front outermost face of building, or the front setback, at 4.5 meters. And then we have the building depth at 15 meters. And then the rear setback at 2 meters. So we are now going to define the section or the profile of the building. And we are going to make use of the building height limit of 10 meters. But before we can do that, we have to check the intersecting point between the slope and the outermost face of building, both at the front and at the rear. So let us check whether this intersection and this intersection will have a vertical difference of 3 meters or less. So with that slope, we can compute the vertical difference between those 2 points. And that will form a triangle, and with a base of 15 meters and a height of y meters. So to compute for the y, having a slope of 15%, it simply means that the slope of 15% will be your rise, or the y height, over the base or the x distance of 15 meters. So therefore, 15% equals y over 15 meters, and your y therefore will be 15% of 15 meters, and that will equate to 2.25 meters. And that 2.25 meters is less than 3 meters. Why do we need to determine whether that is, if that is less than 3 meters? Because there is a provision in the code that says that in case the sloping grade, where the edges of the building footprint, AMBF, running perpendicular to the road right-of-way, has a difference in elevation of less than 3 meters, then the highest adjoining natural grade or ground surface, or the finished grade sidewalk surface, shall be considered established grade elevation. So here, in this illustration, it shows that the highest adjoining point versus the lowest adjoining point. If that vertical difference is less than 3 meters, then our building height will be measured from that highest adjoining point, which is your established grade elevation, up to the flat roof or the parapet of a building. So let us apply this to our sample problem. So we have here now our established grade elevation is the highest adjoining point, and then we measure from here the established grade elevation, a BHL of 10 meters, and that will be the topmost level of the building, so that we can now draw the profile of the building. So this is now how it will look, no? The section of your building. So the next thing that we are going to determine is from the center line of the road here, what will be the angular plane. And so we are going to refer to this table 7.G.3. This is the recommended angles or slopes for the angular planes originating from the center line of the road right-of-way. And for an R1 use or occupancy, and with a road right-of-way width of 12 meters, our angle is 40 degrees from the center line, or with a ratio of 9 meters to 10.5 meters. The 9 meters here represent the rise, or the y, and the 10.5 meters represents the x, or the run. So if you divide 9 by 10.5, it will give you a slope of 0.86, or in percentage that will be equivalent to 86%. So let us draw that angle or ratio of 9 meters is to 10.5. So you will see that some portion of the building now will be cut off because it extends already beyond that angular plane. So let us compute how much is the area, or the triangular area, which will be deducted from the building volume. So that one will have no dimension, so we have to determine what will be the dimension of that triangle, basing it on our initial value of the PHL of 10 meters and the angular plane with a ratio of 9 is to 10.5. So we can see that that angular plane forms a triangle to the outermost face of the building with a base of 10.5 meters. So with that information, we can determine the height of that triangle. So fortunately, the ratio of that diagonal line, 9 meters is the height and 10.5 meters is the base, corresponds to the dimension of our actual base of 10.5 meters. So we can now compute the y at 9 meters. So with that information, we can now find out the other possible missing dimensions. So this is one dimension which we have to determine, because we have already the overall height here of from this point to there at 9 meters, and then from this point to this point is 2.25 meters. Another dimension that we are going to compute is this portion, but this one is very easy to compute because it also forms a triangle. Okay, so this triangle will have a base of 4.5 meters and a slope of 15%. So therefore, we can easily compute for y4, which is 15% of 4.5 meters will give you a value of 0.675 meters. So now we can compute for y3. Our y3 therefore here will be this total height of 9 meters minus this dimension of 2.25 and minus this dimension 0.67. We will arrive at our w3 with a value of 9 minus 2.25 minus 0.675, or a height of 6.075 meters, and we round it off to 6 meters. So with this information, we can now compute for the dimension of this triangle that is to be computed, the area to be computed. From this line, which is our established grade elevation, we have a height of 10 meters BHL, and if we deduct the 6 meters, we can compute for this dimension. That one will give you a dimension of 6 meters. So now we are left with this remaining dimension to compute. Now we have to note that this diagonal line is the same as this diagonal line, having the same ratio of 9 is to 10.5. So this is our y and this is our x. So we can make use of the law of similar triangles, wherein the y over x of a smaller triangle will be the same as the y over x of a bigger triangle. So this is our smaller triangle. This is our bigger triangle having the same diagonal line here, having the same ratio. We can compute for this x distance. Okay, so therefore our x will be this ratio of 9 over 10.5 will be the same as the y of 4 meters over this x distance. So it will be 4 over x will be the same as 9 over 10.5, giving you a value of x here at 4.67 meters. So with this dimension, we can now compute for the area of this triangle, and that will give you an area of 1/2 of 4 times 4.67 or 9.34 square meters. So with this information, we can now compute for the deductible volume of building by just multiplying this area with the width of this building, which is 10 meters. So which means now that our deductible volume will be 9.34 times 10 meters will give you 93.4 cubic meters. But where are we going to deduct this volume? We are going to deduct this from our original volume. We have computed earlier the AMVB initial, which is at 1,500 cubic meters. So to compute now for the final AMVB or the resultant AMVB that is in consideration of the natural light and ventilation requirements along road right-of-ways and front yards, it means that our AMVB will be your initial AMVB of 1,500 minus this deductible volume of 93.4 will give you a final value of 1,406.6 cubic meters. So this is now our AMVB resultant or our final AMVB. So if we are going to show that in three-dimensional view, so this will be the volume of the building. The AMVB of 1,406.6 does not include this portion, no? Because our AMVB, our reference is the established grade elevation starting from here up to the PHL of 10 meters. Now, your final value of the AMVB can be used to compute for the final value of the maximum allowable TGFA, because there is a provision in the code saying that our maximum allowable TGFA must be adjusted so that the AMVB must not be exceeded. Because if it is exceeded, the necessary adjustments on the maximum allowable TGFA must be made, since the AMVB must always prevail. So how is that done? First is to make use of our derived value of the AMVB, the final AMVB of 1,406.6 cubic meters. And then we derive the resultant allowable maximum TGFA average per floor. So we can determine that by just dividing our AMVB final by the BHL in meters. So we have 1,406.6 divided by 10 will give you the average resultant allowable maximum TGFA per floor at 140.6 square meters. And this value we are going to make use to compute now for the final value of the allowable maximum TGFA or the resultant allowable maximum TGFA, which should be your average per floor of 140.6, and multiply it with the BHL in number of floors. For R1, the BHL is 3 floors. So we now have this final value of the allowable maximum TGFA at 421.8 square meters. We can compare this with our original maximum TGFA value that is based on table 7.1. So this is our value from our part 1 of our series. Our maximum TGFA for this lot is 3 by 50% of the TLA of 301 square meters will be at 451.5 square meters. Take note that in this table, there is a provision here saying that This value or figure is subject to reduction to comply with the floor area component of the allowable maximum volume of building, which means that the one that we have derived earlier, our resultant maximum TGFA, is the final value of your allowable maximum TGFA, 421.8 square meters, which will not exceed our computed final value of the AMVB. So that's it, folks. That's it, folks. I hope that you now have a clearer understanding on how to derive the allowable maximum volume of building. Good day, everyone.
Thanks for watching. Don't forget to subscribe, like, and share. For a more comprehensive study on Rules 7 and 8 of the revised IR of the NBCP, please enroll at Atlas CDC Review. Email us at atlascdcreview@gmail.com, or you may join us at our FB group page, www.facebook.com/groups/ALEReview.